Hi, welcome back to another tutorial, and this time we're going to talk about number systems. Okay, these are the number systems that we as humans use, and most importantly, as what our computers use. Okay, so these are the following topics that we're going to talk about: the decimal number system, binary, octal, and the hexadecimal. Okay, so these decimal to binary, binary to decimal, and so on and so forth, these are conversion methods that we're going to do. So if you're presented with a decimal number and then you need to convert it to binary, you will know what to do. Okay, so to start with, so as an introduction, each number system is associated with a base or a radix system. So this is how we know that what kind of number system is the number is. So if example, if the number is 10 and then the radix or the base is 10, okay, 10, and then the radix is 2, that means it is not actually a decimal, but it actually is a binary number. Okay, to know more of it, we're going to proceed with the next slides. But as you can see here, an example for that is decimal base 10. So these are the numbers for decimal. Anyway, we're gonna be able to identify that because we're going to have some examples of this. By the way, MSD stands for most significant digit. Okay, most significant digit, and the least significant digit is the LSD. Okay, so most significant digit means if the digit is considered let's say for example your number is 0 100, okay, 100. Okay, your most significant digit there is the, which one is the 1? Okay, because it signifies that it's the biggest number, or it's the big, it signifies that from that digit is how what the value of the number is. Yeah, anyway, you're going to understand that all the more as we go through the next slides. Okay, so these are the number systems. So again, decimal, binary, octal, and hexadecimal. So in the decimal, base 10, binary is base 2, octal is 8 from the term oct, ocho. Okay, so octal or 8. Hexadecimal is 16. Okay, so how about the symbols? So if it's decimal, all the numbers from 0 up to 9. Okay, so you don't include 10 there for decimal. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. For binary, only numbers zeros and ones. There's no 2, 3, 4, 5, 6, 7, 8, 9. So it's all zeros and ones. Octal is 0 to 7. So there's no 8 there. Okay, even if it's octal, there's no 8 there because you're actually counting. There are 8 kinds of number. So 0 is a part of that. So if you count 0, 1, 2, 3, 4, 5, 6, 7, there's actually 8 kinds of numbers there. I'm sorry, 8, yeah, 8 numbers there. So if counting 0, 1, 2, if you count it with your finger, so 0 is 1, 1 is 2, 3 is 4, 5 is 6, 7 is 8, and so on and so forth. Okay, up to 7, you have actually a total of 8 numbers. And then hexadecimal is 0 to 9. Okay, but there's no 10 anymore because 10 stands for A, 11 stands for B. Okay, 11 stands for B, 12 stands for C, 13 stands for D, 14 stands for E, and 15 stands for F. A is 10, A, B, C, D, E, F. Okay, so A stands for 10, B 11, and so on and so forth up to F. Okay, up to F only. We're gonna have some more examples of that so that you will better understand that in a while. Okay, so the question is, which numbers are used by the next column? Which numbers are used by humans? The only one that is used by humans is the decimal, yes. Okay, and then the others are no. How about computers? Ones that are used by computers are only binary, or zeros and ones. So if given the numbers octal or decimal, if you and then you need it to be understood by human, you have to convert it to decimal. Or if you're given an octal or hexadecimal or decimal, it needs to be used by a computer, you have to convert it into zeros and ones, or in other words, binary. Okay, so these are examples. For zeros, for binary, this is 0, 0, 1, 2, 3, 4, 5, 6, 7. Binary, this is the equivalent. Octal, this is the equivalent. And hexadecimal, this is the equivalent. Notice 7, 7, 7, 7 for octal and hexadecimal. Binary, later we're going to do some computation, and also with octal and hexadecimal. So notice the 7, 7, 7. When for binary, okay, it's going to be, yes, 1 0 0 0. Okay, there's a, we're going to do some computation for that. But notice for octal and hexadecimal, for octal, the 8 now from the 7, remember, 7 7 7. For hexadecimal, 7 7 7 also. For hexadecimal, no problem. 8 is 8, 9 is 9, and then 10 now becomes A. 11 B, 12 C, 13 D, 14 E, and 15 F. But for octal, you notice from 7, 7 7, okay, 7 7, 8 now becomes 1 0. Okay, it starts again with 0, but you have now the 1. So 0 1 2 3 4 5 6 7. Okay, so this is what it's it with another, you call this a prefix. Okay, so you have now the 1. So 1 0 1 1 1 2 1 3 1 4 1 5. Guess what's next? 1 7. Next is 2 0 now. 2 0 2 1 2 2 2 3 2 4. You get the idea. Okay, so that is in the octal. So for the hexadecimal, let's go back to the hexadecimal. So 15F. So what do you think is the next for 16? So 16, it starts with 0 again, but you now have the 1. Like the octal earlier, you have the prefixes ones. So hexadecimal 0 1 2 3 4 5 6 7 8, but with the 1, we have the next. We went back. Okay. So you get the idea. So it's going to be 1 8 1 9, and then 1 1 1A. Okay, 1A 1B. So that's what happens with the hexadecimal. Okay, so I hope you got the idea, but it's not also required for you to memorize the equivalents, because you can actually do a computation for this, which will really come in handy when you do solutions already. Okay, so there. Common number systems. Okay, we went back. Okay, sorry. So this is now like a diagram of if you want to convert to decimal to octal, decimal to hexadecimal, or so on and so forth. Okay, the possibilities. But there's an easy way of doing this. Okay. Okay, let's have a quick example. So 25 base 10, this is decimal. And the equivalent of that, this is base 2, this means this is binary. This is 8 base 8, this means that this is octal, and this is base 16, this means that this is hexadecimal. Okay, so there's a computation for that. Okay, so for the um, this is how we convert the for the decimal. Okay, if you can still remember this in your high school or in elementary, so you have here the least significant digit, which is 5 raised to the power of 0 times 10. Okay, because it's on the right side, so it's an LSD, or least significant digit, up to the most significant digit, which is 1. So 0, as you go 5 to 1, you also have the exponents times 10 as 0, 1, 2. So equals to 5, equals to 20, equals to 100, and then when you add that, you have the 125. Okay, so this is in decimal. Okay, so that is let's now have the binary to decimal conversion. Okay, so the technique is you multiply each bit by 2 raised to the power of n, where n is the weight of the bit. Okay, the weight is the position of the bit starting from 0 on the right. Okay, like what we saw earlier in the example, and then add the results. So let's have an example here. So example, like what we have earlier in the decimal. Now this is the binary. So you have here, so our aim here is going to convert this 2 to 10 or decimal. So this is binary because this is 2, this is the decimal. So how do we do that? So since we are using the binary, okay, so we use the base 2, okay. So 1, which is starting with the right, okay, 1, that's 1 times 2 raised to the power of 0, and then next digit is 1, that is why we have this 1 times 2 raised to the power of 1, okay, and then 0, which is this one, times 2 raised to the power of 2, and then 1 times 2 raised to the power of 3, 0 times 2 raised to the power of 4, and 1 times 2 raised to the power of 5. You do a multiplication of those, and then you have this answer. Okay, and then you add that, and after adding that, you have now the equivalent decimal value. Okay, this is from binary to decimal. Okay, remember that. Okay, so let's go to the next one, which is octal to decimal. Okay, octal to decimal. So the technique here is again just the same. Multiply it by 8n, where n is the weight of the bit. The weight is the position of the bit starting from 0 on the right, and then add the results. Okay, so you see the process is actually the same. Okay, so now before we had this as times 2 because it's from binary. Now because it's octal, we have this times 8. Okay, so 4. Okay, 4 raised to the power of 4 times 8 raised to the power of 0, 2 times 8 raised to the power of 1, 7 times 8 raised to the power of 2. Okay, so if you can raise to the power of 2, which is equals to, you have this 4, 16, and then 448. Okay, and then when you add that up, 416, 448, and you have that decimal value of 468. Okay, so if you're asked to convert the 724 octal to decimal, the answer now is 468. Okay, you see the trend. Okay, when you are trying to convert it to decimal, that is the process. You take note of what base it is, okay, and then you if it's 2, so it's going to be times 2. If it's if it's binary, it's times 2. If it's octal, it's times 8. So you know what happens if you do it in hexadecimal, okay, which is base 16. So instead of those numbers, you have times 16, which we will have on the next one. Okay. Okay, so that is from octal to decimal. Okay, now let's go to the next. And now we're going to that was octal to decimal. Now we're going to the hexadecimal to decimal, as what I've mentioned before. And I think you know what's gonna happen here, okay, which is to multiply each bit by 16 to the n, where n is the weight of the bit. The weight is the position of the bit starting from 0 on the right, and then you add the results. Okay, hexadecimal to decimal. So as you can see, it's ABC. Okay, ABC, where A is 10, B is 11, and C is 12. Okay, so as you can see here, C times 16 raised to the power of 0, so 0, 1, 2, and so on and so forth. That's how that's the order. So B times 16 to the 1, A times 6. So we get the equivalent of this, which is C, which is 12, B is 11, and A is 10. So we do the math of 16 to the 0, 16 to the 1, 16 to the 2. So 1, 16 to 56, you multiply it, and then you have this value for your decimal. From hexadecimal, ABC is actually equals to 2748 in decimal. Okay, so I hope you don't forget how to convert any of the number systems to a decimal. You always use its base. Okay, so if it's binary, it's base 2. If it's octal, it's base 8. If it's hexadecimal, it's base 16. Okay, okay, that was hexadecimal to decimal. And then next now is from decimal to binary. Okay, now from the decimal to binary, so this is how we do it. Divide by 2 and then keep track of the remainder. First remainder is bit 0. LSB is least significant bit. Second remainder is bit 1, and etc. Let's have the example so that you can understand it fully. So we have here a decimal to binary, 125 decimal to binary. How do we do that? We divide it by 2. So because it's binary, it's base 2, that's why we divide it by 2. 125 divided by 2, and what's the answer? It's going to be 62, and there's a remainder. So 1, you keep track of the remainder, and then 62 divided by 2, the answer is 31. There's no remainder, so you make it 0. And then 60 divided by 2 is 31. There's no remainder. 31 divided by 2 is 15, and there's remainder. That's why we have this one. 15 divided by 2 is 7. Okay, and there's a remainder 1. That's why we have this one. And then 7 divided by 2 is 3. Okay, remainder 1. That's why we have this one again. 3 divided by 2, and the answer is 1. There's a remainder 1. We still have to divide this last one. 1 divided by 2 is 0, and remainder is 1. Okay, so the first one on top, okay, the first one, we don't do the 1 divided by 2. The answer is not 1/2, but with this kind of division, the answer for that is 0, because in binary there's only, I'm sorry, the explanation is that if the last number is 1 and then divided by 2, the answer will always be 0. Okay, and then you have to put the remainder 1. Okay, so if that is the case, so the first remainder is going to be the uh, least significant value or least significant digit. Okay, as explained on this least significant bit. Okay, LSB, I'm sorry, LSB, least significant bit. So the first remainder goes to the rightmost, and then the last one goes to the MSB or most significant bit. So you read this 1 1 1 1 1 0 1, and then you have it here, and then the don't forget to put the base, or else it may be mistaken as also as decimal. Okay, this is what lets us keep track as to what kind of number system you are using. You have to always put the base. Okay, so again, how did we do that? 125 divided by 2, the answer is 62, and then there is remainder 1, that's why we have this 1. 62 divided by 2, the answer is 31, and then there is no remainder, that is why we have this 0. 31 divided by 2, we have this 15, remainder 1. 15 divided by 2, the answer is 7, remainder 1. 7 divided by 2 is 3, remainder 1. 3 divided by 2 is 1, remainder 1. And then lastly is 1 divided by 2. Okay, 1 divided by 2. As long as there is a whole number, you keep on dividing it until it is 0. When it's 0, that's enough already. Okay, so that's how to convert from decimal to binary. And the next one is octal to binary. Okay, so octal to binary, how do we do this? Okay, technique is convert each octal digit to a 3-bit equivalent binary representation. To have this as an example is this. Okay, so 705 to binary. Okay, you have this, you have to separate this as a, each digit will be represented by a binary. Okay, so that means you have to convert your binary to your this 7, okay, to binary. Okay, so 7058. So how do you get the binary of the 7, and how do you get the binary of the 0? How do you get the binary of the 5? Okay, for a while, let me just check on the next slide. Okay, so to represent this, for you to be able to get this as easy, the easiest way possible is, I'll like to show you how to compute for this shortcut method. So Microsoft Excel. Okay, so for example, this is 7, 0 and 5. Okay, so which is represented by 1 1 1, and then 0 0 0, and then 1 0 1. So how do we do that? You have to 1 2 and 4. Okay, this is like a guide for you. Okay, that on top of the binary values, okay, on top of example, this is the 147. Okay, I'm referring to 7. This is 1 1 1 1 1 1. That is because since it is marked as 111, you add the values 4 plus 2 plus 1. That's why you have it equal to, let me move this, equals to, sorry, equal sign, okay. So that's why we have this, because we added, because this is marked, all the 4, 2, and 1 is marked as 1, so you add the 4, 2, and 1. The answer is 7. Okay, how about the 0? Okay, if it's 0, so I'm gonna remove this. So 0, 0, 0, you will not be adding any of the 4, 2, and 1. That's why your answer is 0. How about the 5? Okay, so let me just remove this, no fill. How about the 5? So that you will know what I'm referring to. How about the 5? How do you get the 5? You add 4 and the 1. So you have 4 plus 1 is equals to 5. That's why you have this 101 as the 101. Okay, so another example, 3, 2, and 8. There's no 8, actually there's no 8. 3, 2, and 6. So for 3, how do you get it? The 3. How do you get the 3? You add the 2 and the 1. So that means you have to put 1 here and 1 here. So this is 0. So that means the value for your binary is 0, 1, 1. Okay, for 2, how about for 2? So of course this is the only one, so you put a 1 here, so the others are 0. So the answer now is going to be 0, 1, 0. Next is for 6. Sorry, you need to really be able to, let me just make this very clear. It should always be 3 digits, okay, so that this won't change anything. I will put some. So this is, again, let's start with the 3. 3 is, how is 3? This is 1 and 1, so that you have 0, 1, 1. Okay, 0, 1, 1. Let's have this in the middle. So for 2, of course, this is the only one, so the others are 0, 0. So the answer is 0, 1, 0. And then for 6 is, of course, we're going to add the 4 and the 2. 4 and the 2, and then the other one is 0. So the answer is now 1, 1, 0. So the equivalent value of 326 in octal, this is octal. Octal is equals to what? 0, 1, 1, 0, 1, 0, 1, 1, 0 in binary. Okay, so let me just again 326 space. So here it is. 326 octal is equals to 0, 1, 1, 0, 1, 0, 1, 1, 0 in binary. Okay, I hope you understood, you were able to get that. Okay, so going back, so that is from octal to binary. You group them by, so each number will be represented by 3 binary, so and so on and so forth. So octal to binary. Next one is octal. We're done with that. Hexadecimal to binary. Now, if octal it's 3, in hexadecimal you're going to group it by 4. Okay, convert each hexadigit to a 4-bit equivalent binary representation. So, same with the octal, but now we have to group it by 4. Okay, so we now have, let me go back to my Excel. So, Since this is octal, you only have the 4, 2, and 1. Okay, 4, 2, and 1 only for the octal. So since it's going to be hexadecimal, this is now going to be 4 groups. This 1, 2, 3 bits. So in hexadecimal, since you have 4 bits, 1, you multiply by itself. Okay, 1 times 2 is 2, 2 times 2 is 4, 4 times 4 is, I'm sorry, 4 times 2 is 8. Okay, sorry. So times 2. Don't multiply it by itself, but you multiply it by 2. So 1 times 2, you have 2. 2 times 2 is 4. 4 times 2 is 8. So this is now our 4-bit representation for the hexadecimal. That is why, for our example, you have there 1, 0, AF. Okay? Okay, let's have this 1, 0, A, and F. Let me just move this here. Okay, 1, 0, A, and F. So, as a solution for 1, of course, we mark this only as, so the only one that has 1 is here. So, all the others are 0, 0, 0, 0. So, that is your answer for 1. 1, 2, 3, 1. For 0, of course, it's all going to be, let me just change this to text so that it won't automatically convert. So the answer, it should always be, remember always, it should always be a 4-digit. Okay, so for 0, of course, you will have all zeros, 1, 2, 3, 4. For A, which is actually number 10, which is actually 10, so you add 8 plus 2. So 8 plus 2. So all the others are 0. So the answer for A is 10, 1, 0, and 1, 0. And finally, for F is, what is F? F is actually 15. So you add, actually if you add 8, 4 plus 2 and 1, and it's going to be equals to 15. Okay? So the answer now is 1, 1, 1, 1. So that's the solution for the 10AF16 or hexadecimal to binary. You always represent each number as a 4-bit. Okay, so I hope you understood that. Let's go to the next slide. Okay, so next is decimal to octal. Earlier we had octal to decimal, so divide by 8. Okay, so if it's just like what we did earlier from decimal to binary, we divide it by its base, which is 2. Now since it's octal, we divide it by 8. Okay, so 1, 2, 3, 4 decimal to octal, so 1, 2, 3, 4 and divided by 8, put the remainder. Okay, so the answer is 154, and then remainder 2. So same process, the least significant bit is the first one, so 2 goes here, 2 goes here, 3 goes here, and then the 2 goes here. Okay, remember again, this is decimal to octal. Earlier we had decimal to binary, we divide it by 2. Now since it's octal, we divide it by 8. And same process of doing it, okay, until you get a 0. Until you get a 0, that's the time you stop. Okay, and your answers are actually the remainder. It's not these answers, but the final answer for your conversion is actually the remainders. Okay, so please don't forget that. Another is decimal to hexadecimal. What do you think is gonna happen? Just the same process. If it's from decimal to another number system, you divide it by the base. Okay, so since it's hexadecimal, it's base 16, so divided by 16, and you keep track of the remainder. So here 1, 2, 3, 4 decimal to hexadecimal. Okay, so 1, 2, 3, 4 divided by 16, remainder is 2. the answer is 77, and then remainder is 2. And then 77 divided by 16, the answer is 4. There's a remainder 13. And then finally, it's going to be 0. 4, you cannot divide it, so the answer is 0. Okay, and whatever is what you did with the dividing is going to be the remainder, the last one. Okay, so remember the 13. Okay, the 13 in hexadecimal is not present. You have to convert it to its equivalent, which is letter D. Remember, in hexadecimal, it's 1, 2, 3, 4, 5, 6, 7, 8, 9. A, B, C, D, E, F. F is 15, so you get it. A is 10, D is 11, and so on and so forth. So your D here, your 13 is actually B. That's why you write the answer 1, 2, 3, 4 decimal is equals to 4D2 in hexadecimal. Okay, so how about binary to octal? That's easy. We do the opposite thing. Okay, what we did earlier. Okay, group bits in 3 starting on the right, convert to octal digits. We do the reverse now. Okay, so earlier when octal to binary, okay, we represented each digit as 3 bits. But now you are given, okay, you are given first a binary of convert it to octal. What you do first is you group it by 3 from the right. Okay, you group it from 3. That's why you have 1, 2, 3. This is one group, this is one bit. That's why you have this. And then 0, 1, 0. That's why you have this. And then 1, 1, 0. You have this. And finally is 1. And then you convert that to as what we did in our Excel. Let's have that. It's the reverse thing now. So let me remove this first. So remember, we have the octal, so we have 3 bits. So fill. So our values are 1, 1, 1, and then 0, 1, 0, and then 1, 1. Sorry, 0, 1, 1. This is supposed to. Let me just change the formats here so it won't change and convert it to anything else. There. So 1, 1, 1, 0, 1, 0, and then 0, 1, 1, and then 1. So of course the 1, 1, 1, if you put the 1, 1, 1, is actually 7, and then 0, 1, 0. So 0, 1, 0, sorry, is actually equals to, this is the only one, this is 2. Okay, and then how about the 0, 1, 1, 0, 1, 1. So you add the 2 and the 1 because they are the ones with the 1. Okay, so 2 and the 1, so it's equals to 3, and finally is 1 only. So of course it's understood that this is 1 and then the others are 0. Sorry, that's 0. So of course the answer is going to be 1. So basically your answer is 1327 in octal. Okay, so hope you got it. So the next one is binary to hexadecimal. So the same process, it's just the reverse. So group bits octal, you group, always remember if it's octal you group bits by 3, but if it's hexadecimal, binary to hexadecimal, or vice versa, it's always grouped by 4. Okay, so the example here is this. So again, you always start with the right, so you group it by 4. 1, 2, 3, 4. This group is here, and then 1, 2, 3, 4, another one, and then 1, 2, and then this one. So after grouping it, you convert it now to whatever equivalent it is in hexadecimal. So let's have that example here. So the first one is 1011, 1011, and finally is 10. So of course, if you add the 8 1 and 1. 8 plus 2 plus 1 is actually equals to 11. Okay, the answer is 11. And 11 is, there's no 11 in hexadecimal. Remember, your hexadecimal is up to 9, and then so you won't forget is the number for hexadecimal is 1 to 9, and then you have the, sorry, okay, let me just change that again. I'm sorry, text, so there will be no conversion. So again, your hexadecimal numbers is 1 up to 9, and then you have now A, B, C, D, E, F. This is 10, this is 11, 12, 13, 14, and 15. So for this particular one, which is equals to 12, so sorry, that's 11. 8 plus 2 plus 1 is 11. So this is it. That's why the answer is B. That's why we have it as B. It's not 11. So same thing for this, it's B. And then finally is 1, 0, or 0 and then 1. So that is 2. So that means this is 2. So this is B, 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 and 2. Okay? So 2BB. So you have now the conversion. This binary to hexadecimal is, the answer is this. Okay? So octal, how about octal to decimal? Now this becomes more interesting for this. For this, you have the binary as an intermediary. You have to convert it first to binary and then you group it. Okay? So let's have this. This is octal to hexadecimal. You convert this first to binary, and then after that you group it. Remember 16, you group it by 4. Okay? So 1076 octal, you convert it to 16. It has to pass first to a binary conversion. So let's have that example. So let me just remove this and this also. So 1, 0, 7, and 6. You have to convert this to what? To binary first. Okay, this is octal, remember, ha? Octal, you convert it first to binary. So 6 is 4 plus 2. So 1, 1. This is 0. So 1, 1, 0. For 7, this is going to be 1, 1, 1. Again, why? You will ask, sir, because the ones with the 1 are the values that you will be adding. So 4 plus 2 plus 1 is 7. That's why you have this here as 1, 1, 1. For 0, of course, it's all going to be 0. So 0, 0, 0. So the answer now is 0. And of course, for the 1, you have this all as 0 and then this one as 1. Okay, so your answer is 1, 2, 3, 1. So, oops, sorry. The format cells text. To avoid any changes, it always goes back. So this is, since this is 1, 2, 3, in octal, remember it should always be 3 digits. 1. So 4, 0, 1, 2, 3. 3 digits. Now we have to group this. After this is now binary, you have to group this now by 4. Okay, this is binary already. You have to group this by 4. That means this will be converted to 0. The first grouping is 0, 1, 1, 1. Okay, so 0. Okay, remember this is the one that we will be grouping. Okay, so the first one is, let me just make this bigger. There. So again, the first step is convert it to binary, and then the next step is the binary answer. You have to group it by 4, because remember in hexadecimal the binary is going to be grouped by 4. So the first grouping is 0, 1, 1, and 1. This one. So I'm gonna write it. So there's 1110. 1110. So next is this one here. The first one here is already in this group. So this is the next. So 1100. So there's 2000 and 11. Okay, so again, this is the first group, and then 1100 is the second group, and then the next one is 0100. So that means you have two zeros and then one, then 0. 1201. Do you understand that? I hope you got that. Okay, this came from this. We group these bits here by 4. Okay, so we now have this binary groupings, and we now convert it to, again, I'm gonna copy this, put this here, paste, okay, so that we'll get the equivalent. So 111 1110. So you add the 8 4 and 2. What's the answer is 14. So what is 14 equivalent to? It's E. Okay, E, because remember, let me put that back here. So this value is 8 plus 4 plus 2 is 14, and then I'm gonna remove this so you won't get confused again. This is the one that we're referring to. 14 is actually E, so this is going to be E. Okay, the next one is, this is the only 1 1, and then this is 0 0, so we add the 2 and the 1. So 2 plus 1 is actually equals to 3. And then finally is the 0 0, this one, okay, 0 0 1 0. So the answer is 2, because this is the one that's highlighted. So the answer is 2. So 2 3. This is our final answer. Okay, 2 3 E. That's why we have this here on our example. It's 2 3 and then E. Again, convert it to binary, group it by 4, 1 2 3 4, 1 2 3 4, 1 2 3 4, and then you get the equivalent hexadecimal value. Okay, so hope you got that. So same process for hexadecimal to octal, it's just a reverse. You get the binary again, you get first the binary and then group it by 3 now. So 1F0C16 to 8, you convert this to binary. Again, how do you convert it to binary? Let's go back to our, now it's hexadecimal. So it's a group of 4. So C is a group of 4, 0 is a group of 4, F is a group of 4. So if you convert that, so let's have that here. So C, 0, F, and 1. So your C is actually, what is C equivalent to? C is 12. Okay, 12. So you have to get a combination of 12. So for us to get 12, so you add this 8 plus 4 is 12. Am I correct? So I think I'm correct. So the answer for let's move this up. I'm gonna move this up here. So the answer is 1100 for the first C. And then of course the 0 is 4 zeros, 1 2 3 4. And then the F, you know what F is? That's 15. So automatically 1 1 1 and 1. You add 8 4 plus 2 plus 1 is 15. So 1 2 3 4 5. Sorry, 4 only. And then 1, so of course 0 0 0 and 1. There. So from this, let me go again. It changed back. Format cells, text. So this is 0, 1, 2, 3. Sorry, 0, 1. So this is 1, 2, 3, 4. So from this, you group this by 3. Okay, so as you can see here on the example, this is the 0011, 0011, 000, 00, and 1111. That is 7. And then so you put a bar from the right. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And then now you do the math again. Now with the 4, now with this already, with the 1, 2, and 4. Okay, so let me go back there. So this is 4, because this is 4, 2. Above here is 4, 2, imaginary 4, 2, and 1. This is 1, because 4, 2, and 1. And then another 4. And then 4, 2, and 1. You add 4, 2, 1 is 7. That's why it's 7. 4, 2, 1. This is 1 and 0. So the answer is 17414 octal. Okay, from hexadecimal to octal. Okay, guys. So I think that's the last topic that we have for conversion. So I hope you understood it. The only thing here is you really need to practice some more numbers for you to be able to understand it all the more. And you can do that. You can do some supplementary in the internet, get some examples, and then do the solution. Don't do the shortcut method by just typing. There's actually a calculator for conversion, which is a very lazy way of doing it. You do it step by step, because in the quiz or in the exam, you will be required to show your solution. Okay, guys, thank you so much for listening. This concludes our lesson for today. And I hope that you'll be able to apply this in the exercises, quizzes, and the exam. And thank you so much for your time. Have a nice day, and God bless us all. Bye.